All right, let's pull back the curtain on something we see every day but almost never think about, how the world around us actually gets built. We're going to dive into engineering's secret blueprint, that hidden thinking that turns a wild idea into a real, tangible thing. I mean, think about it for a second. How do you make something from nothing? It feels like it must be magic, right? Or maybe the work of some lone genius who gets hit by a lightning bolt of inspiration. But the truth is, there's a powerful, repeatable method behind it all. So let's get into it. We're going to look at engineering design not as some mysterious art form, but as a science. It's a systematic approach, a way of thinking that anyone can learn and use to solve some seriously complex problems. This quote really gets to the heart of it. Great design isn't just a happy accident, it's a strategy. And that strategy is built on a rock-solid understanding of the fundamentals. And that, right there, is where we're going to start. So, you've got this massive, complicated problem. Where do you even begin? How do engineers not get completely overwhelmed? Well, they start by making it simple. They treat the unknown solution as a black box. The first tool in their toolkit is this idea of a system. Think about anything, really. Your car, a coffee maker, a whole power plant. They all have inputs like electricity or coffee beans, and they all have outputs like your car moving or a fresh cup of coffee. That line between the outside world and the thing itself is the system boundary, and everything inside, well, that's the puzzle we have to solve. And what's wild is that no matter how complex the system is, it's really just shuffling around and converting three basic things: energy, like electricity from the wall; material, like water or steel; and signals, like the data flying to your phone. That's it. And this leads us to a really critical idea: function. And listen closely here, because this is important. A function is totally abstract. It describes what the system needs to do, not how it's going to do it. We're not thinking about gears or wires or code just yet. We're only focused on the goal. This is where it all starts. All we know, all we care about right now, are the inputs we have and the outputs we want. Everything in between is just a mystery inside that black box. And that's actually a good thing. It frees your mind to focus purely on the problem without getting tangled up in the details of the solution just yet. Okay, so we've got our mysterious black box. How do we go from that to an actual concrete plan? Well, we start by cracking that box open. We take that one big main goal and we start splitting it into smaller, bite-sized tasks or functions. Now, to make this all feel a bit more real, let's use an example from our source material. The problem is this. We need to design a machine that can pack carpet tiles. So the input is raw carpet and the output is a nice, neat box of finished tiles. That's our overall function. So what has to happen inside that black box? Let's break it down. First, we need to stamp the tile shape. Then we have to check if it's a good one, check the quality. After that, we need to count the good ones until we have enough for a box. And finally, we pack the whole lot. See, we just created a sequence of subfunctions. That's what designers call a function structure. But, it's never quite that simple, is it? We have to separate the core tasks, those are the main functions we just listed, from all the other little jobs that have to happen to make the main ones possible. And those are called auxiliary functions. Think about it. For our tile packer, we also need a way to get rid of the scrap pieces after stamping. We need to physically move the bad tiles out of the way. We got to bring in the empty boxes and tape. And we need to send a signal when a box is full. These aren't just nice-to-haves. Without these auxiliary functions, the whole process grinds to a halt. So far, everything's been pretty abstract, right? We've just defined what needs to happen. But now comes the magic. How do we turn these abstract ideas into real, physical things that you can actually touch and that actually work? The answer is something called a working principle. This is the bridge that connects the world of ideas to the physical world. It's a simple recipe. You take a law of physics, a physical effect, you give it a specific shape and size, that's its geometry, and you choose the right material. That combination is what makes a function come alive. Let me give you a couple of examples. Let's say our function is to amplify force. We can pick a physical effect we know, like the lever law. Then we give it a geometry, a handle with a pivot point, and boom, we have a working principle, a lever. Or, say we need to make electrical contact. We could use the physical effect of thermal expansion. Apply that to a bimetallic strip, which is a specific material and geometry, and now we have a strip that bends when it gets hot to close a circuit. See? From abstract goal to real thing. So we've got the process down,
But what about the person doing it? What kind of mindset does it take to actually walk this path, all the way from a fuzzy problem to a finished working solution?
While great designers are masters of two kinds of thinking, first, there's discursive thinking. That's the logical, step-by-step, organized process we've been talking about. But then there's intuitive thinking. That unconscious aha moment, that flash of insight that seems to come out of nowhere. The real genius is knowing how to switch between the two, blending methodical work with creative leaps. And research shows that the best problem solvers all have a few things in common. They have a ton of knowledge, but it's organized in their heads so they can find it fast. They know exactly when to think abstractly and when to get down to the nitty-gritty details. They're comfortable with uncertainty, and maybe most important of all, they never lose sight of the goal, but they're always flexible about how they get there. Now that you know the blueprint, you're going to start seeing it absolutely everywhere. This systematic approach isn't some obscure theory. It is the invisible architecture holding up our entire modern world. That engine in your car? It's a mind-bogglingly complex system. But it was designed by breaking it down into sub-functions for fuel, for air, for combustion, for exhaust, all built from very specific working principles. What about that smartwatch on your wrist? It's a system, right? It's converting energy from a battery and signals from space into a material output, light on a screen, all based on a precise structure of functions. Even that massive bridge you drive over every day is a product of this exact same thinking. It's the solution to the function transfer loads safely, and it's realized through physical effects like tension and compression applied to very specific materials and geometries. Look, this way of thinking isn't just for engineers building bridges or cars. It's a powerful tool for solving any complex problem you face. It takes creation out of the realm of magic and turns it into a process, a method you can actually follow. So, now that you know the secret blueprint, the only question left is, what will you build?